All right, students, this is part 1 of a series of 2 videos on types of chemical reactions. In this video, we will cover synthesis, decomposition, and combustion reactions only. There are actually 5 major types of chemical reactions. We will discuss these 3 in today's video and leave single and double replacement reactions for part 2. So before we begin talking about the types of reactions, I just want you to know that in this video today, I'm not going to be giving you balanced reactions, just so that you can focus on what's happening and less on the numbers that are out front. All right, so the first of the 5 classes of chemical reactions is synthesis reaction, also called combination reactions. And a synthesis reaction is where you have 2 or more reactants combining to form only one product. So here are a couple of examples of synthesis reactions. So you know they're synthesis because you only have one product or one compound on the right side of the arrow. All right, so before we talk about the 3 subtypes of synthesis reactions that I expect you to know, let's talk a little bit about a rule that's going to come up a lot in this video. And this rule is called the Brinkelhoff rule. And the Brinkelhoff rule basically states that these elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, and notice that they're all nonmetals, when they're all alone, meaning they're in their elemental form, so not bonded to anything, they can't exist as single atoms. They are always diatomic. So notice that it's never just Br, it's Br2, an I2, an N2. Diatomic means there's 2 of them bonded to each other. So this rule is going to come up a lot when we're predicting products of reactions. So keep in mind the back of your head, the Brinkelhoff rule. All right, so let's talk about the first subtype of synthesis reactions that you are expected to know. Okay, the first is that if you have 2 single elements, both nonmetals, when they combine, they will combine to form a covalent compound. You already know that. So here's an example of a nonmetal, 2 nonmetals, N2 and H2, and remember our Brinkelhoff rule, N and H can't exist as single atoms, so they're diatomic. So when they're alone, they're N2 and H2, but when they combine, they form ammonia, NH3. Remember, these are unbalanced equations. So these types of synthesis reactions where you have 2 nonmetals forming covalent compounds are pretty tricky and they're hard to predict products for. And the reason why is because these 2 nonmetals could combine in a number of ways. They could produce NH3, but they can also produce N2H2 or just NH2 or a whole bunch of different compounds. Because we're not matching them up by ion charges because they're not ionic, they're very tricky to predict products for. So I won't ever make you predict the products of 2 nonmetals joining into a covalent compound. All right, the second subtype that you would need to recognize for synthesis reactions are simple reactions where you have a metal and a nonmetal. And of course, you know that a metal, when they bond to nonmetals, will form ionic compounds. So an example would be the formation of aluminum oxide. So you've got aluminum, which is your metal, and oxygen, which is your nonmetal. And remember Brinkelhoff, that's why O2 is doubled, will produce aluminum oxide. Now, you will be expected to predict products of a metal joining with a nonmetal because you've done it before. So for example, you might see something like this, where you have sodium and sulfur, and then an arrow, and then you're expected to write the formula for the product. And you can do that based on ion charges. So even though over here these are not ions, when they join, you know that they're going to ionize and form an ionic compound. So that means that your sodium is going to end up with a +1 charge, and your sulfur will end up with a -2 charge. And I expect you to remember your ion charges from before. And so if that's the case, if these cross down, so your 2 ends up here and your 1 ends up here, you are going to end up with Na2S, and your charges are going to go away because they cancel out. So your formula for your compound is Na2S. So you've just predicted the product of that reaction. So I'm going to star that so you know that that's one of those that you're going to need to be able to predict products for based on ion charges. All right. The last type of reaction or of synthesis reaction that I would expect you to recognize and be able to predict products for is where you start with a metal oxide and water as your reactants, and that's going to produce a metal hydroxide. So let's talk about what a metal oxide is. A metal oxide is going to contain a metal and oxygen. So for example, MgO. Mg is your metal and O is oxide. And of course we all know what water is, H2O. And that's always going to produce a metal hydroxide. So the metal is going to be the same metal that you started with. And then hydroxide is a polyatomic ion that is OH with a -1 charge. And so in this case, we're going to end up with 2 hydroxides bonded to our magnesium because of ion charges. So metal oxide plus water will produce metal hydroxide. Will be expected to predict the products of a metal oxide combining with water to produce a metal hydroxide. And to do that, you need to know your ion charges. So let's do this example. So potassium oxide and water. So we know, we can identify hopefully that we have a metal oxide and water. We know that our product is going to contain the metal, the potassium, and hydroxide. We know this much. Now we need to look at the charges on the ions. So your potassium is always a +1 charge and your hydroxide is a -1 charge. So if we were to cross those down, we'd just get one of each of those. So we don't need any subscripts, and then we can get rid of our ion charges because they cancel out. So this would be the appropriate product for the reaction between this metal oxide and water, just potassium hydroxide. So I starred that one as well because you will also need to know how to predict the products of a metal oxide combining with water. All right, so just so you know, that's all of synthesis right there. All right, let's talk about the second type of, or class of chemical reactions, the decomposition reaction. So a decomposition reaction is when you have one reactant and it is going to break apart into 2 or more products. And you might notice that this looks very similar to what we just looked at. That's because it's the opposite of a synthesis reaction. It's the reverse of a synthesis reaction. Whereas a synthesis, we took 2 and combined them into 1. This is now taking 1 and breaking it into 2. You should know that these types of reactions often don't just happen on their own. They require a little help in the form of energy or a catalyst. So you might see over the arrow something like a triangle for heat, or you might see maybe something like this, lambda nu, which means light. I mean, it needs light to do what it needs to do. Or over the arrow, you might see a chemical formula written. So for example, you might see like KMNO3 over the arrow, something like that. That indicates that that's a catalyst that's required for the reaction to take place. So these are both examples of decomposition reactions, and they're really easy because decomposition reactions always start with one reactant and produce more than one product. So the big clue that you have a decomposition reaction is only one reactant. So as with synthesis, there are 3 subtypes of decomposition reactions that I expect you to be able to recognize and predict products for. And they're the exact opposite of what we just did for synthesis, so they should be relatively easy. So the first is where we have a covalent compound, like say water, breaking down into two nonmetals. So don't forget your Brinkelhoff rule when you're predicting the products of these reactions, because if you have nonmetals that are single, some of them are diatomic. Not all of them, but some of them. So again, you will be expected to predict the products of these types of decomposition reactions. So for example, you might have something like P2O4. You know this is a decomposition reaction because you only have one reactant, and I might ask you to predict the products of that. Well, you know it's going to be phosphorus and oxygen. Now, the only thing you need to remember is Brinkelhoff. So phosphorus is not part of Brinkelhoff, but oxygen is, so you just need to make sure you put that O2. So we'll go ahead and star that because you will need to know how to predict the products of a reaction like that. All right, so you would also be expected to recognize when an ionic compound breaks down into a metal and a nonmetal. For example, zinc phosphide, when it decomposes or undergoes decomposition, because it's one reactant, it will break into two products, zinc and phosphorus. And again, you need to remember Brinkelhoff on these. Phosphorus is not a Brinkelhoff element, nor is zinc, so we don't have to worry about making it diatomic. And of course, you will be expected to predict the products of a reaction like this. So we'll put a star next to it, and let's do an example. So we might have something like this ionic compound made of rubidium and sulfur. And it's going to break down into, of course, rubidium and sulfide. Neither one is a Brinkelhoff element, so you don't need the subscript 2s. At this point, you might be wondering, well, what about this 2 right here? And like up here, we had some subscripts that disappeared. That's where we would then go back and need to balance this equation to account for the fact that over here we had 2 rubidiums and over here we only have 1. But we're not balancing equations in this video, we're only predicting products. All right, let's do the last one. All right, so the last subtype of decomposition reaction is again the opposite of what we learned for combination or synthesis reactions. So a metal hydroxide will break back it down into a metal oxide in water. So for example, barium hydroxide, you can decompose it into barium oxide and water. You, of course, will be expected to predict the products of a reaction like this, so let's do an example. So you have silver hydroxide. So we know that this is going to break down into a metal oxide and water. Well, the water part's easy, so you've got one of the products. Now, the second product, a metal oxide, is an ionic compound. It contains a metal and a nonmetal. So we know the metal is going to be silver, and we know that it's going to be oxide because that's what a metal oxide is. But we need to look at ion charges. So silver is always a +1, but oxygen's a -2. And if you were to cross those down, you would get 2 silvers to your 1 oxygen. And then, of course, you'd want to erase your ion charges because they cancel out and go away. All right, so there's an overview of all of your decomposition reactions. All right, and last but not least, everyone's favorite, mine included, combustion reactions. So combustion reactions are actually really easy because they all follow a pretty similar format. So you always have something called a hydrocarbon. Now, hydrocarbon will react with oxygen to produce carbon dioxide and water. So you always get carbon dioxide and water as your product, and you always have O2 and a hydrocarbon as your reactants. So hopefully you're asking yourself what the heck a hydrocarbon is. A hydrocarbon is any compound that contains some amount of carbon and some amount of hydrogen. Now, often hydrocarbons contain oxygen as well, which would still result in the same products, carbon dioxide and water. So of course the numbers of carbons and hydrogens or carbons, hydrogens, and oxygens in your hydrocarbons can vary, but if you have a hydrocarbon plus or reacted with oxygen, you will always get carbon dioxide and water. So here are 2 examples of combustion reactions. So CH4, methane, that's natural gas. It's what we use in the lab whenever I have you use the Bunsen burners. So of course, if you ignite it in the presence of oxygen, you are going to produce carbon dioxide and water. Or this right here, cellular respiration, where you take glucose and in your cells you combine it with oxygen and produce carbon dioxide and water. And you should probably know that most, if not all, combustion reactions actually result in the production of a little bit of heat as well. We just don't usually write that in the chemical equation because heat's not a chemical, it's an energy. And of course, you will be expected to predict the products of a combustion reaction, which should be really simple. So let's do a practice. So you look at this reaction and hopefully you realize that it's not decomposition because you have 2 reactants, and it's probably not going to be a synthesis reaction because neither one of these is a single element or a metal oxide and water. And so hopefully you recognize this is a hydrocarbon because it has carbon and hydrogen in it. And this is oxygen gas. And in your head, hopefully you're like, oh, I know the products of that. That's a combustion reaction. You will always get carbon dioxide and water for those reactions. And those are easy peasy lemon squeezy, easy to reduce or to remember the products for because they're always the same 2 products, carbon dioxide and water. Now, we should mention, because we're good students and I'm a good teacher, now, some hydrocarbons contain other things besides carbon, hydrogen, and oxygen. Like some hydrocarbons will also have sulfur, some will have nitrogen, some phosphorus. Sometimes you get lead, like in gasoline, which is a hydrocarbon. So that means that not only are you going to produce carbon dioxide and water in those reactions, but you're going to get sometimes a 3rd or a 4th product. I would not expect you to be able to predict what that product is, but I may ask you to predict at least these 2, because you should know that a hydrocarbon and oxygen will always give you at least carbon dioxide and water. Remember, easy peasy, lemon squeezy. And then the last one will be given to you because that's sulfur is also going to produce a compound with oxygen, but you aren't expected to know what that one is. All right, so there's all of combustion right there. And of course, here is the entire presentation in a nutshell. Stay tuned. In part 2, we will discuss the last 2 types of reactions, single and double replacement.